Okay, so session is being recorded now. This is going to be the second practice exam. So I think this one on Google Drive is called Extra Practice Exam 1. Yeah, Extra Practice Exam 1. The first problem starts with two current carrying wires. It says magnetic force and current. That's the first problem for you guys to reference that. The first video is already uploaded on YouTube from this morning. With captions and everything, subtitles all ready to go. And this will be the same here later this evening. But let's go ahead and get started with problem 1, magnetic force and current. So we have two current carrying wires. They carry equal currents of 10 amps in opposite directions as shown in the figure. Each wire is 50 centimeters long. And the question is, what is the net force, magnitude, and direction on the top wire, right? So first off, when they're asking for magnitude of force, right, we're looking for this FB, this magnetic force, right? And at the same time, right, this magnetic force is going to be like dependent on the magnetic field generated by the current carrying wires, as well as like the characteristics of the wires. So like the length of the wire is going to make a difference. The current that it's carrying makes a difference. The magnetic field that's generated will change the magnetic force. So an easy kind of like relationship that we can observe here is to use that equation that we have on our equation sheet, which is the magnetic force for a current carrying wire is equal to the current times the length of the wire, right, times the magnetic field generated by the wire, right? So really the key thing to understand here is when we're looking for magnetic force on a specific wire, what kind of values do we plug in, right? So if we're looking for the force on the top wire, right, it's what that top wire feels. So what the top wire feels. So that means that when we're looking at our equation, FB is equal to I times L times B, we're looking at, okay, well, what's the current that's being generated by that wire, right? Because that's an inherent characteristic of that wire. Then we look at the length of that specific wire, because those are characteristics that will pertain to that specific wire. But then the magnetic field is what kind of changes around. So we don't use the magnetic field of that specific wire. We use the magnetic field generated by the other wire, because then that wire is kind of like in the magnetic field of the other one, and it feels that other magnetic field, right? So we're not concerned with what that current generates or what that wire generates. We're concerned with what it feels, right? So if you're looking for force of the magnetic force of the bottom wire on the top wire, so FB bottom on top, then we're concerned with the current of the one on top, I top, the length of the one on top, because those are two inherent characteristics of that specific wire. But then we're concerned with the magnetic field B bottom, right? So we're concerned with the magnetic field of the bottom wire, because that is going to generate that magnetic field that the top wire feels, right? So that's kind of similar to the electric force stuff, right? And electric field. So you're kind of looking at how that wire will react to, or how it, like what it feels based on the other wire, basically. So when we're solving that problem, right, we have I, our current is 10 amps, the L, the length, each wire is 50 centimeters long, so that's fine. So 50 centimeters, we're gonna make that 0.5 meters instead. And then we have the magnetic field generated by the bottom wire, right, which is what the top wire is going to feel, like I said. Now, to figure out this magnetic field of the bottom wire, right, then we have to use the equation for the magnetic field of a current carrying wire, which we did a similar problem like this in the last exam. We take the permittivity constant, right, and then we multiply it by the current, and then divide it by 2 pi r. So once again, in this case, we're going by the values that were, I guess, the values for the bottom wire now, because we're looking at the field, the magnetic field generated by the bottom wire. So we take that permittivity constant, which is 4 pi times 10 to the negative 7. We multiply it by the 10 amps that is going through that bottom wire, and then divide it by 2 pi r. Now, r here refers to the distance or the specific point away from the wire, right? So in this case, the top wire, you can see in the diagram, is 4 centimeters away from the bottom wire. So that is kind of like our r here, that 4 centimeter distance, because we're trying to look at that 4 centimeter point away, that top wire, the location of the top wire, what kind of magnetic field it feels from the bottom one. So in that case, we plug in 0.04 meters for the radius for that equation here. So if we do that, 4 pi times 10 to the negative 7, and then times your 10 amps, and then divided by 2 pi times 0.04 meters, right? Then we should get, what is it, 50.2 roughly, times 10 to the negative 6 Teslas, right? So that's our magnetic field. And then we can just simply plug that in. What was it, 50.2? Yep, 50.2 times 10 to the negative 6 Teslas for our magnetic field in that equation, right? And then that's just simply what the magnetic force would be, right? So we can just calculate that, and we should get around like 2.5 times 10 to the negative 4 newtons here. I think so. Could I borrow someone's calculator real quick just to double check, because I want to make sure that this stuff is right. But essentially what's going on here as well too, like it's also nice practice to do this, but it's not required of the problem. So if we look at the if we want to look at the magnetic field generated by the bottom wire, so the bottom wire has a current this way, right? It's to the left, it's moving to the left. So that's the direction that our thumb is going to be pointing in. So if we wanted to figure out what the magnetic field is, right, at that point, at the location of the other wire, the top wire, right? So if I draw this on the board real quick, we have a wire here, wire there. This one has a current going to the left. This one has a current going to the right. Now, if I'm looking at this bottom wire, once again, the bottom wire is going to be generating that magnetic field, and the top wire is going to be feeling that magnetic field. So when we calculate the magnetic force, like I said, we want to be looking at what the bottom one generates, and that's what the top one feels. So the force is always what it feels, right? Force F feels F, right? And so for practice, have your thumb in the direction of the current, right, for that bottom wire. It's the left. And then you can kind of wrap your fingers around at the top part of the wire, right, or above that bottom wire. And so anything above that bottom wire is in the realm or the location of that top wire, right? So anything above that bottom wire here, whatever direction you get is what type of direction for the magnetic field that is felt by the top wire. So if I have the current pointing to the left, if I wrap my fingers around, I should see it hitting into the page, right?
That fits it if your fingers are above?
Yeah, so if you're above, exactly. So if you're above, it's hitting into the page, right? Into the wall, into the page, into the table, like that, right? And so that means if they were to ask you, okay, what is the direction of the magnetic field at the location of the wire? Well, the wire is above the bottom one, right? The top wire is above the bottom wire. So that means if we try to, oops.
What if the wire is vertical? Is it just the same thing?
If the wire is vertical, yeah. So
was like,
if the wire is vertical like this, same idea, right? Let's say the current is going upwards, right? Let's say the current is going upwards. And if you're looking to the right of that wire, upwards, and you wrap around into the page over here, right? So if they were to ask you, for example, to draw this as well, because they could ask you to draw the direction of the magnetic field or something for a current carrying wire, then remember that X's denote into the page, and little dots or circles will indicate out of the page. So if they told you, okay, what's the direction of the magnetic field to the right of the wire, then that's into the page.
So you just draw an X.
So you just draw a bunch of X's over here,
Oh, okay.
right? Now over here, it goes into the page on the right, wraps around, and then comes out of the page to the left. So then you'd have like a bunch of dots like this, right? So yeah, that's a good question. If you have like a vertical wire, that's how you would draw it as well. So it's always into the page on one end and out of the page on the other end, just depending on like what points you pick and then how your fingers wrap around. Does that make sense?
yeah.
But yeah, that's it. Yep. So that's how to figure out the direction for that stuff, and that's a good segue into the next problem. Problem 2 here says 4 charged particles are traveling in circular orbits in magnetic fields with field directions as noted. The tangent vectors indicate the particle velocity at a specific point, which particles have a negative charge. So this is like a copy and paste from one of your quizzes. This exam right here is like my exam that I took. So this was what you guys got on your quiz was like an old exam question essentially. So they have these. Wait, actually, you know what? I'll sit and draw this first, and then I'll draw it up on the board. But basically, you have this first circle over here. You have a particle kind of moving down and to the right, so that's in the clockwise direction in that case, and you have into the page everywhere. Well, I guess kind of misleading. It should be just in the middle of the circle, really, what they're talking about here, but it's fine. Anyway, so you just have clockwise, right, velocity, and then you have into the page for your magnetic field for circle A. For circle B, you have counterclockwise velocity, right, and you have into the page as well for your magnetic field. For circle C, you have out of the page clockwise, and then for circle D, you have out of the page counterclockwise, right? So I kind of mentioned this in the other practice exam, but basically you want to look at things as to how it'll match up with the right-hand rule and how it'll match up with the centripetal motion of a circle, right? So in this case, the goal is to have it constantly moving in a circle and at the same time add up with the right-hand rule. So if I grab circle A, right, it's supposed to be moving in this clockwise direction, right? So first of all, it's kind of weird to do this, right? But basically, you kind of have to, I don't know, hold up. I just want to make sure that I'm getting this right because I have to contort my hand and fingers in a different direction. But basically, for that first A, you have your velocity kind of this way, right? Your velocity this way, and then your magnetic field is pointing inwards. So it's like you have your thumb pointing down into the right, kind of. And actually, you know what? I'm stupid. There's no reason to do that because it's all clockwise. So you can just pick the top point of the circle or the bottom point of the circle. So if it's clockwise, then at the bottom of the circle, your velocity is moving to the left. So that means that thumb is moving to the left, index finger is into the page, and then your force is downwards. So that would indicate, right? That would mean for a positive particle, the force would be downwards, right? So is a downwards force, is that what's needed to have that circular motion in this case? Not quite. Because if we're, yeah, go ahead.
Is it because it's an electron?
So it'll be a negative particle. Now the reason why it's a negative particle is because, like I said, I mean, if you have that clockwise motion with the magnetic field pointing into the page, at the bottom of the circle you're going to have the particle moving to the left, right? Magnetic field inwards into the page, and then your magnetic force is going to be pointing downwards. So we want the force to be pointing upwards, central to the circle, right? Radially inwards to maintain that circular motion.
So it should be the exact opposite.
So it should be the exact opposite, right? So if it were a negative charge, it were to have a upward force, and if it has an upward force, that matches with the circular motion that we want, because we always want the force to be pointing inwards towards the middle of the circle. So the condition first off is to have the force pointing towards the center of the circle, and if it's not, right, based on the right-hand rule, then you know it's a negative particle, right? So for A is a negative particle because once we do the right-hand rule, we realize that the magnetic force is pointing, at least at the bottom of the circle, it's pointing downwards when it should be actually pointing upwards, right? So because there's that discrepancy, we know then that has to be a negative particle because a negative particle would have the exact opposite direction of the force as the right-hand rule. Alternatively, and we talked about this earlier, right? You could use your left hand, right? I don't 100% advise it because you can throw things off, but you could also just kind of look at things like, all right, well, if I use my left hand and the particle is moving to the left, right, and you have your index finger pointing into the page for your magnetic field, right, Then you have, with your left hand, your magnetic force is pointing upwards. So that checks out to use your left hand, technically. But like I said, it's not 100% advised because you're sticking with your right hand for everything. And you might as well just stick with that and then just kind of flip the direction whenever you have to. But that's the idea here. Like, I think sometimes it's hard to like move your fingers around and stuff to figure it out. But I think that's probably the best bet is to try and do with your right hand and then flip it.
X means into the page, right?
Yeah, X's are into the page and then circles are out of the page. Are you guys here for 132, right? Okay, just making sure. Let's see here. So with that being said, for B, right, we're on the second practice exam, the extra practice exam one. I don't know if you guys have that.
Is this on your drive?
Yeah. What was I gonna say? So for B, if we're looking at B now, right, then you have motion of the particles counterclockwise, right? So if we just look at the top, for example, if we just choose like the top part of a circle, then we see that the particle is moving to the left, right? And now it's still the magnetic field is into the page, right? So like that. And now your magnetic force should be pointing downwards, which we need it to point downwards because that'll be pointing towards the center of the circle at the top, right? So that checks out. Magnetic force pointing towards the circle, cool. Adds up with the right hand rule, awesome. So we're done. So we know that B is a positive particle. Otherwise, right, same case as A, right? If we had the other direction clockwise, then the magnetic force would not be pointing towards the center of the circle, and that would mean you'd have a negative particle, right?
Wait, could you repeat B again? Sorry.
Yeah. So since we're moving in a counterclockwise direction, right, you can just choose, like you don't have to really contort your fingers to like point like this and do that. Like you don't have to do that. But the idea is that you can just pick one point of the circle that makes it easy for you to use the right hand rule. So if you're at the top point of a circle, particle moves to the left, that'll be counterclockwise, magnetic field into the page, and then your magnetic force is downwards, right? And we need it to point downwards because that helps with the circular motion, right? It always has to be pointing radially inwards towards the center of the circle. Does that make sense?
So just, that's what B would look like, basically?
Yeah, that would be the force. The force of B would be pointing downwards, and then basically like that would indicate that it's a positive particle because whatever force is generated matches up with the direction of the centripetal force needed, right? Because in this case, your magnetic force is your centripetal force, right? So kind of moving down the list, if we look at C now, right? C is moving clockwise direction. So if we choose the bottom point of the circle, you're moving to the left, right? And then you also have the magnetic field pointing out of the page, right? So it should kind of look like this. You see that?
So, wait, this is C, right?
C, yep.
Yeah, I was looking at it, it's like, it's weird.
Yep, so it should be like pointing to the left, right, for your, let me draw it up here. So, the bottom point of the circle, left, right, and then you have the magnetic field out of the page, right? So your index finger should be pointing out of the page. So the left, out of the page towards you, and then
So you're just
what do you
visualizing
see?
it.
Exactly.
Wait, so how did you?
Yeah. So let me. I know it's like that's really difficult. I was telling you earlier, like if you play an instrument, like it's a lot easier to like do this.
So it's kind of
So yeah, it's easier to do, right? Because your like fingers are all spread out and stuff. So if you do, here, you do this, right? Here's your thumb, and then you want to kind of flip this like that, and then your middle finger should just kind of be pointing in the natural direction like that.
So yeah, the finger just.
Exactly. Nope.
So this would just be a negative charge, like it's pointing upwards.
No, because you're at the bottom here, right? So this is pointing upwards towards the center of the circle. So it wouldn't be a negative charge. This would be a positive one because it matches with the right hand rule. Because the right hand rule will always tell you what the direction of the magnetic force is for a positive particle. And in this case, if you're moving to the left, magnetic field outwards, out of the page, and then magnetic force is upwards, and we want that magnetic force to be upwards, pointing towards the center of the circle, right? So the idea is that if it doesn't point towards the center of the circle, like once you do your right hand rule, if it's not pointing towards the center of the circle, you know it's a negative particle.
Oh, that's why the dots matter. Like the
Yeah, the dots will matter for determining the direction of the magnetic field, which is your index finger. Do you guys have any questions about like this stuff so far, or don't be shy? Okay. Now, D, right, is going to be the same thing. You choose a point at the top of the circle. That'll be where the particle is moving to the left. Left, out of the page, upwards. So that shows that at the top of the circle there, the magnetic force would be pointing upwards, which is not what we want. We want it to be pointing downwards towards the center of the circle. So that indicates that D is a what?
positive charge.
Bro.
No, negative.
Negative charge the other way around. Let me see here.
Are you
I'm
going to
trying
do
to
the
think.
practice exam?
Yeah,
Or-
practice exam. What do I want to say? It's probably an easier way to like do this. You could. No, that doesn't work. Maybe try with your left hand.
Oh,
Try with your left hand. Maybe that works. Like left towards you and then like that.
Oh, wait. Yeah, that's different.
Oh my god.
it's like
It's
a
so
weird gang signs.
yeah. There are enough gang signs all like all class.
Wait,
Okay. But yeah. It just kind of takes practice,
Practice.
and you gotta like try and like stretch your hands, crack your knuckles if need be, because you're gonna have limited space during the exam, so you need to like really like do some stretches or something. I'm not like even joking. I swear, like I would do this before the exam. Like I just like stretch my fingers out and stuff so I can have room to like. But yeah, it just takes practice. The more problems like these you do, the better you're gonna get at being able to form your fingers at exact 90-degree angles. But yeah, I mean, it's practice. Do you have a question? Okay, cool.
Question.
So in that case, A and D are the ones that have negative particles because their magnetic forces do not match up with the right hand.
So, if, considering it's pointing inwards, we would expect it to be pointing up, but since it points down, that's why we consider it to be a negative charge, basically.
Wait, say that again?
Because of D, how we would expect it points inwards, we would expect it to point up.
Well, it's not inward. So like your magnetic field's out of the page, right?
Oh, out of the page.
Because it's circles. So you're moving to the left, it's out of the page, and your magnetic force points
Oh,
upwards.
so it should move up, but since it's moving down, that's what.
Well, it's not moving down. It's like it's all moving in a circle. The idea is that to maintain that circular motion, remember like in physics 131 where we had centripetal force? So we want a force that's pointing always towards the center of the circle at every single point, right? So even if I got like, if I'm looking at this point here where it's downwards like this, right? I'm looking at downwards, and then I have, let's say, oh, that's gonna be bad. Okay, that's fine. If you pick this point here where the particle is moving downwards, and then you have your magnetic field kind of like outwards like this, then you should see that the magnetic force points away from the center of the circle, points this way. You see what that's not a good point to pick, but like, I'll just stick with the top one. So the particle's moving to the left at the top, that counterclockwise direction, right? Then you have particle moving this way, magnetic field pointing outwards out of the page, and that means your magnetic force would point upwards if it was a positive particle, right? But we want the magnetic force to point downwards to maintain that circle, to offer some kind of centripetal force. And so, because a positive particle would actually have magnetic force upwards, a negative particle would have a force that points downwards, which is towards the center of the circle.
So that's why we want to pick the ones where the force is upwards. That way we can.
Well, it's not always upwards, because you could have at the bottom, right?
Yeah.
You could have at the bottom, like this way, like that, and then upwards. If you're moving, well, hold up, at the bottom would be clockwise, so, my bad. So at the bottom, since you're moving that counterclockwise direction, right? So you're moving counterclockwise this way. So at the bottom, your velocity is to the right, right? Your velocity is to the right. So if your velocity is to the right, and then your magnetic field is pointing outwards like this, then your magnetic force points downwards.
Okay, so
See
we
what I
want to
mean?
pick the ones that either point up or down, basically. That way we can flip them. Basically.
Yeah, at these two positions, yeah. We want here, like whatever you get here has to point downwards, whatever you get here has to point upwards.
Oh, because it's
Right? Because it has to point towards the center of the circle. But I mean, like, you could also think about it here or here as well. Like, the idea is that you just have to have it pointed towards the center of the circle, right? It's not a matter of up, down, left, right, because you could pick like a point here. You could do that kind of, you know, at an angle. But the idea is that it has to kind of, you see here, like, it'll have to point this way, right?
Yeah.
So that's the idea, that it points towards the center of the circle always. If it's not pointing towards the center of the circle by the time you do the right hand rule,
it's negative.
it's a negative particle.
Okay, so the ones that if they don't point towards the center, then it's
Yeah,
negative.
if they don't point towards the center, then it's a positive, or it's a negative particle. Damn it.
There's
But
9
yeah.
combinations.
Does that make sense so far?
Yeah, that makes sense.
Mm-hmm. All right, so we have magnification now. Problem 3. So that is an object is placed 30 centimeters in front of a converging lens with a focal length of 10 centimeters. And it's asking what is the magnification of the lens. So object distance, right, that is 30 centimeters. And they gave us the focal length, f, is 10 centimeters, right? And they said this is a converging lens. So for a converging lens, do you have a positive or a negative focal length for a converging lens?
Converging positive or negative?
For a converging lens.
Negative.
Other one.
Positive.
Right?
Oh, yeah,
For
diverging.
diverging, remember diverging will create virtual images. Convex mirrors will create virtual images. So those will have negative focal lengths, right? So this is going to be still a positive focal length of 10 centimeters. Now, if they're asking for magnification, remember the equation for magnification is negative di over do. So it's negative of the image distance divided by the object distance, right? So, could you guys just? I'm sorry, I don't mean to like just because I'm recording this session as well, so it's fine. I just want to make sure that everyone can hear it, but you're good, no worries. But we have negative times the image distance divided by the object distance, and so we have the object distance in this case, but we need to figure out what the image distance is, right? So using the thin lens equation, right, we have 1 over the focal length, 1 over f, is equal to 1 over do plus 1 over di, right? So our object distance is that 30 centimeters, and object distance is always positive, right? Because it's a real object, so it's always positive. And then 1 over f, our focal length is 10 centimeters. So now we're just left with trying to figure out what the image distance is. And once we have the image distance, we can plug that into the magnification equation to figure out what our magnification is. So once we do that, right, we should see 3 over 30 is equal to 1 over 30 here, okay, plus 1 over di. So we should see 2 over 30 is equal to 1 over di. So our image distance should be around 15 centimeters.
Where did we get the 3 from? 3 over 30?
Yeah, so let me write it on the board here real quick because I was writing it on the iPad and I just have to keep going back and forth. Where's the cleaner? Where'd the cleaners go? I like just, oh, there we go, thank you. Thank you.
Welcome. Oh no, I'm already done with it.
So you use the thin lens equation, right, where you have 1 over focal length equal to 1 over object distance plus 1 over image distance, right? So our focal length was that 10 centimeters. Oh my gosh. I'm just gonna go get another marker. So 1 over 10 centimeters, right? And that's equal to 1 over 30 centimeters for the object distance plus 1 over di for the image distance. So I just took I subtracted this
the
1
common
over.
factor.
Yeah, so common factor. So this is 3 over 30, then minus 1 over 30 over, that's 2 over 30, and 2 over 30 is equal to 1 over di. So this is 3 over 30. I don't know why all these markers today are 4. So minus 1 over 30
equal to 1 over di, which is 2 over 30.
This is mass and
And then you just kind of flip it, and that's just 15.
Yeah.
Yep. So that's 15 centimeters for the image distance there, right? So with di being 15, we can just plug it back into the magnification equation. Magnification is equal to negative di over dl, so negative 15 divided by the object distance, which is 30 centimeters. So we should have a magnification of negative 1/2, right? Now, what does a negative magnification mean?
It's
Inverted, exactly, right? So it's just a flipped image in this case. And then if you have a magnification that's less than 1, it means that the object, like image, has got smaller. And if it's greater than 1, then the image has gotten bigger, right? Ray tracing for problem 4. So problem 4, this is where I recommend to, what's it called? Determine like all the different combinations of where you can have an object located, right? So if you have, sure. Awesome, thank you so much. I mean, you guys can stay. Like I just wanted to make sure.
No, I don't want to disturb it. So.
No, it's fine. I mean, it's for everyone. It's just that
Because she's choosing online homework, so I'll just do one out there.
All right, cool. So yeah, depending on where you have the object located, especially for a concave mirror, right? That'll change up whether you have a real image or a virtual image, right? So pretty much for concave mirrors, for most locations of the object, you're going to get a real image, except for one location, which is if you have the object in between the focal point and the mirror, that's when you have a virtual image as a result. So you kind of have like, oh, this is nice, okay. So if you have your focal length here, right? If you have your object over here, over here, over here, over here, over here, whatever, right? It's going to be fine. It's going to always result in a real image. But if you have the object in between the focal point and the vertex of the mirror here, that's going to cause a virtual image, right? That's like the only scenario for a concave mirror where it's going to cause a virtual image. And so if you look at that problem, right, problem 4, you'll realize really quickly that even without doing ray tracing, right, let's say you screw up the ray tracing or you don't know like how to do it or whatever, you forget, then you might lose 3 points of the ray tracing. But if you know this kind of like rule here, right, and if you're aware of like the different combinations that you can get with concave mirrors and with converging lenses, then you can see that, okay, well, it's between the focal length and the mirror. That means it's small, upright, virtual. There's like different like combinations of the different images that you can get. I've outlined them all on the PowerPoint slide that I had for this chapter, as well as I sent some links in the GroupMe and the Discord when I was studying for the MCAT with combinations like all these different like scenarios, like whether you have, because you could have, for example, the object at the focal length, in which case I believe there's no image formed actually at that point. You could have it at the center of curvature, you could have it between the center of curvature and the focal length, and that'll cause different types of images. They might be like flipped versus not flipped, larger versus smaller, stuff like that. So there's a table that I sent out in the Discord, and then I have that kind of information in the PowerPoint slides as well. But what do I want to say? So now that kind of solves part B for that problem, that it's small, upright, and virtual. Or is it, hold up, did I mess it up? I think it might be larger, yeah. Hold up.
So something like this would be,
Let me see.
just make sure I did this.
I think so. Yeah, that looks good to me. Let me draw the rays out here. So for these, this is a concave mirror, right? So when we draw these rays, we have, do they give us a center of curvature here? Stuff like that.
Mm-hmm.
I mean, it doesn't really matter all that much, I
You
guess.
give us a
but-
focal point and a center.
Mhm. So for this one, you can have, obviously you have here your optical axis, right? You can have one ray that kind of goes from the object to the center of the lens itself, and then perfectly kind of like reflects this way into a V shape. And so I call this one V for Vendetta. So yeah, anyway, that's like a V shape, right? And then that's how you can kind of visualize that, right? And then, let's see here. It's another easy one that I could do.
Back to the future.
yeah, we could do Back to the Future, right? So we have start at the object, you go straight to the mirror, parallel to the optical axis, right? And then you would just kind of like, what's it called? Just go to the focal point, right? So you just go through focal point this way, I believe. I'm gonna double check that just to make sure because I forget sometimes how to draw these rays. So let me double check here. Okay. Alright, looking it up here just to make sure that I didn't screw up those rays. Yeah, so you should have it directly parallel to the optical axis and then it goes back to the focal point. That's why I call it Back to the Future. Now in this case, like I said, the reason why they kind of seem to like diverge like that is because it's the object is between the focal point and the mirror, right? So it's gonna produce a virtual image. It shouldn't actually like converge at a real point, right? The light rays don't come together at a specific real point. They only seem to originate at like other points. And so in this case, right, what you would do kind of is like draw dotted lines essentially.
Where they would be.
Where they would be, right? So with the V for Vendetta line, what you do is that you draw it straight to the middle, right? And then your reflected ray, you draw dotted lines like that straight along the same kind of axis.
Yeah, where they would.
Until it hits another ray, right? So here, for the Back to the Future ray, you have the parallel line, right, along the optical axis, and then it gets reflected across like that, right? So you draw your dotted lines based on the reflected ray, right? So it kind of like, once they connect, it's kind of poor, but anyway, something like that, where you can see clearly that it's going to be larger and
So it's
magnified,
large,
obviously.
Large upright version.
Yep.
Nice.
And I want to double check this as well, just to make sure.
It's basically like this. This will make.
Yeah, yep. And you only have to draw 2 rays as well. You don't have to draw all 4. As long as you pick 2, like you can pick, honestly, like pick your 2 favorite ones, the easiest ones to draw, and you just can go by that as well. But yeah, that looks right.
So
And then-
that's small, upright, and virtual, right?
I had it larger, my bad. So I said small, upright, and virtual on accident. It should be larger, upright, and virtual in this case.
Yeah.
But yep, so I have it. You guys can take a look at it here. This was on my exam, so I drew it like this. I had 1 ray. Let me up the brightness here a bit. Where's that? I don't know. Can you guys see that?
Yeah.
Right. So Eric, do you want to take a look as well? And Matthew, if you want to come over and take a look. But yeah, so basically I had ray parallel to the optical axis, right? And it goes immediately down and then through the focal point. And then the other one, V for Vendetta, through the center of the lens or center of the mirror, and then perfect V downwards again. And then you base your dotted lines on like the reflected ray. So like the second one that you draw. So you don't just continue drawing a dotted line like this. It's based on the one that's been reflected. So you just kind of draw it like that, and you draw this one because it's the reflected ray like that. So you draw your dotted lines.
Like a hypothetical.
Exactly. So hypothetically, right, like if we were to extend that line the other way around, like behind the mirror, then that's how it would be drawn. Does that make sense? But yeah, and I don't know, I could share like my work for this exam, just so you guys can see like thought process and whatnot. Some of the problems I did them a little wrong, so obviously you can just refer to the answer key for that, but for the most part, like I did solid on the exam. Let's see here. So, yeah. So in this case, you can see that it's larger upright and virtual. Virtual because, like we said, it's going to be located between the focal point and the mirror. So it's going to produce a virtual image. And you can see even with the ray tracing, that kind of confirms it because the rays won't converge at any real point. And then once you kind of draw where they would theoretically like land or originate from, then you can see that you get a larger image.
I'm a bit confused how you got it to the. I'm trying to do the focal point, but it doesn't seem to. Maybe that's just. How did you get it to?
So you have that one, you have to the right like that, and then you have it go through the focal point. Yep, excellent. And then,
But it kind of goes.
Okay.
Yeah. How,
Interesting. That's odd. I don't know if you just have it like at a slightly different angle or something. Do you mind if like we just erase like do you have an eraser or something? I just want to double check. Because depending on how you draw it a little bit, like your angle might be a little off, and so that'll cause like a little bit of confusion. That's why I don't like the ray tracing stuff. But yeah. Okay, so let's see. So there's the object. So we'll have it drawn like this, and then go like straight through the middle like that, and then we'll have this one go through here, and then like this. Like your two triangles kind of have to be the exact same kind of do that?
yeah.
So kind of, I think the problem was with this V for Vendetta one,
Yeah.
right? So you want to have it where like, it's not a very sharp V, it's more of a wider one, where it perfectly cuts the thing in half, right? Perfectly cuts the optical axis in half. Like you have to like almost like a very perfect V, to where that. I think the good measure for it is that if you have your object like this, right? If I were to flip my object, it would like perfectly flip and intersect with this like line over here. But yeah. So I can essentially just take a screenshot here real quick and copy and paste this into the document to show people. Let me drag this over. But yeah, so basically you have your object, direct parallel line to the optical axis, and then through the focal point like this, and then another one from the object height to the center of the mirror, and then like perfect V like that. And you should have kind of like a dotted line, and that shows that you have a bigger object that's upright, and is going to be virtual because the rays don't actually converge, they seemingly originate behind the mirror. Now, that's problem 4, right? Problem 5 now, what did I want to say? So, problem 5 is nuclear binding energy, right? For the nuclear binding stuff, if you just know your equations and you understand like how to apply all this stuff, all the terms and the vocab associated with it, it should be a breeze for the exam. They should be easy points because it doesn't require you to actually like explain anything really. You just need to understand like how to use all of the equations and stuff, because you'll get to I don't know if you were here when we were doing this, but yeah, I think you weren't here, but we did the last problem on the first exam, which was the nuclear binding energy stuff, and they had something called what was it? something biological effectiveness. It was RBE, relative biological effectiveness. So like that's such a weird like term, and a lot of people, if you haven't read the reading, you might not know what it is. I don't know if it was mentioned like in the lectures. Probably was the RBE stuff, right? So with that, right, there's a definition, there's a whole background and fluff and whatnot in the reading. You don't have to necessarily understand like what it is or like the background of it. You just need to know like how to use the equations with it, honestly. Like it's one of those things, like, you know how with the first unit where you had the what's it called? I keep forgetting what was the last thing that you guys did for the first unit with thermodynamics. Oh man. Boltzmann's constant stuff. That's what it was. So that was like just plug and chug. Like it was a lot to know, a lot of complex equations, but as long as you knew the equations, you were fine. Like you didn't have to understand all the Boltzmann's like stuff behind it, right? So it's the same thing here. So as long as you know how to use the equations, you're fine. So for 5, it says an atom, a carbon-14 atom has a mass of 14 atomic mass units, so it's like 14.032. It says calculate its binding energy per nucleon, right? So for binding energy, there's a specific equation for that, and it's very common. It's E equals mc squared, right? So now we're like using the equation that everyone talks about, but like no one knows how to use, and now we know how to use it. So our binding energy is equal to mc squared, right? E equals mc squared. Now this mass, right? This mass is going to be the change in mass that you observe for the system, and so that is consisting of the total mass of the hydrogens, total mass of the neutrons, and then minus the atomic mass number that you have, right? So it's like adding up protons and neutrons and subtracting by your atomic mass to get the change in the mass. So like for the mass of a proton, they kind of substitute the mass of a hydrogen atom for that, which kind of makes sense because you always hear about like H+ atoms and whatnot being treated as just a proton. So with that, this M is going to be a delta mc squared, right? So it's going to be made up of how many, like all the different like changes that we have for the mass. So we have 6 protons here, right? So that's 6 times the mass of a hydrogen atom, right? So 6 times like 1.008, and they have these values on the equation sheet. They're like more specific values. Like I think it's specifically 1.007825 is what they have for the atomic mass of the of a hydrogen atom.
Oh yeah.
So it should be on the other side. Let's see here. Someone said it was on here. It should be. Okay, flip the other page maybe. I don't know.
Yeah, no.
Really? That's interesting. Wow. All right, well, I take that back. Then you probably should know the mass of a hydrogen atom and a mass of a neutron. They're like very close anyway. Like one's 1.08 and one's like 1.008, and the other one's like 1.009 almost, right?
So you can just use one basically.
Yeah, almost. You can kind of use one. I don't know. I'm not sure why they didn't include it in the equation sheet, because they usually use the more specific values for them, because you're trying to adjust kind of like for the difference in the mass number and whatnot. But yeah, I think if you guys would just want to go ahead and write them down and just have that, because you could just very well just have that memorized like before the exam and just write it on your equation sheet like shortly before. So the mass that they generally want you to use for a hydrogen atom is going to be 1.007825 atomic mass units. Here, I can blow it up for you. This one. 1.007825. And let me write it up on the board as well. So mass of hydrogen, 1.007825, and then mass of a neutron is like 1.00865. So So those are the two mass numbers that I think you should know for this stuff. So for the change in mass, like the delta M, right? Like I said, it's going to be just the sum of this stuff. So it'll be the number of hydrogen atoms, right, times the mass of the hydrogen atom, and then plus number of neutrons, right, times the mass of the neutron, and then minus like your total atomic mass number. And that's your delta M. Like this is your delta M here. So if we have a carbon 14 isotope, right? Carbon 14 has 6 protons, right? So how many neutrons would it have if we're dealing with 14? So that's the atomic mass number of 14. So how many neutrons would it have?
6 now. Oh,
6 protons. So for if you have an atomic mass number of 14, then
8.
8, right? So you just subtract the atomic mass number by the number of protons, and that helps you get the number of neutrons, right? So you'll often see the notation for the isotopes as like some element, right? Say like platinum or something, and then A, that's your like atomic mass number, right? And then Z is your number of protons, right? So just so you know that like when you see that notation on the exam, that's what it means. Like if they're asking, okay, they might literally just ask you like what's A and what's Z. And so that is your atomic mass number, this is your number of protons, right? So you can subtract the two, you take like 14 minus 6 in this case to get the number of neutrons, right? So in that case, like I said, you take the number of hydrogens times the mass of hydrogen plus the number of neutrons times the mass of neutrons minus the atomic mass number that they gave you. So we'll do 6 hydrogen atoms, right? Or 6 protons in this case because we're approximating the proton using a hydrogen atom. So 6 times that 1.007825, and then plus 8 times 1.00865, right?
Neutron.
And that's for a neutron, exactly. And then we subtract by the mass that they gave us, which was 14.0032420.
Did you multiply 6 times the number of neutrons, or what did you multiply by?
6 times the number of protons, because we have 6 protons.
Oh, and then 8 times the mass, which is like 1.001.
1.00865. Yeah. So we should have 6 times 1.0078225 plus 8 times 1.00865, and then minus 14.0032420.
And then once we get the 0.112908 times c squared.
Yeah, so you got 0.112908, yep. And then that's times your c squared. So c squared, c is the speed of light. To avoid like doing a bunch of conversions and stuff, because usually they're trying to get you to calculate energy in the end, they just take out the c squared and replace that with 931.49 mega electron volts. So you can just multiply by 931.49 mega electron volts, right? Now, they want you to calculate it per nucleon, right? And so that just means like dividing by the mass number, right? To get the binding energy per nucleon. So whatever you get for that.
What does Mn mean, mass number?
Mass of a neutron.
Mass of a neutron? Oh.
Mn is mass of a neutron. So once you get that like change in the mass, you can multiply by 931.49 mega electron volts, and then whatever mega electron volts you get, you can just divide by 14 in this case, divide by the mass number to get the binding energy per nucleon. So you get like that is 0.11 close. I got 0.112908 unless they oh my bad. I just nabbed your calculator. Okay, so let me double check that. 6 times 1.00785 plus 8 times 1.00865, and then minus 14.0032420. .112908. Yeah, that's what I got still.
I got 0.1139.
You might have like added like messed a number there because you're off by like 0.001. But that's fine. Like, do you you understand like the process behind it? If you want to like take a look at.
Use the full numbers.
Yeah, I use the full numbers. I wouldn't round. Yeah, I would use the whole thing.
Okay.
But once you do that, you can just multiply by that 931.49. That gives you the mega electron volts. And then from that, we're just going to divide by 14. I wouldn't divide by like 14.0032. Like, I just divide by the normal mass number that was given to you for the isotope.
You got 2908, right? That's what I got.
2908. Yep. Mm-hmm. So you just take that 105.17 mega electron volts that you should get from multiplying these two. So 105.17 mega electron volts, and then divided by 14, and that should give you like 7.5 mega electron volts per nucleon, basically. Now they might ask you to maybe convert this to joules per nucleon or something like that, right? Well, now you have mega electron volts, right? So mega electron volts, that's just, so like if this was, once we have 7.5 mega electron volts per nucleon, right? That's 7.5 times 10 to the 6th electron volts, right? Because mega would just be 10 to the 6th of anything. So 7.5 times 10 to the 6th electron volts. And then we know that 1 electron volt is, I think it's like 1.6 times 10 to the negative 19, something like that. Maybe I'm off. Hold up. Let me, don't mind, I can double check that. Yeah, it is 1.6 times 10 to the negative 19 joules. So if you want to convert from mega electron volts, so you have like 8 mega electron volts, and then you want to convert it to just regular joules, then we know that, well, first of all, you write 8 mega electron volts as 8 times 10 to the 8 times 10 to the 6th electron volts, and then multiply that by this. So in 1 electron volt, it is 1.6 times 10 to the negative 19 joules. Electron volt will go with electron volts, and you're left with joules on top. That makes sense? Makes sense? Okay. Yeah, go ahead.
For the next problem.
Yeah.
Would the 120 be... Okay, now we have to use the equation for activities. So would 120 be like our initial value, or would it be like 120 times?
Yeah, 120 would be our initial value. So that's your R0, right? That's your initial like activity, right? That's your decays per
just
second.
120. Now like 120 times n is our initial.
Yeah, so just 120 there, right? So I'll write it out here in a sec. So it says radioactivity. The graph shows the activity in decays per second of a radioactive sample over time. Determine the half-life of the nuclei in days in the sample, right? So what's it called? So we need to do the half-life, right? So they're giving us like values of activity, right? So we know that the activity equation, like RT, right, after some activity after a certain period of time, is equal to the initial activity, right, times what? Let me look at the equation sheet real quick just to double check. So times E negative T, which is our total time, divided by tau, which is our time constant here. Now, this time constant, right, can be expanded and written out in a couple different ways. So usually it'll just be written out as 1.44 times like the half-life, basically, right? So our R0, our initial activity is going to be 120. That's the initial decays per second, because that's where the graph starts. So that's 120 times E raised to the negative like elapsed time, right? So this elapsed time was what they showed from 120 to 15. It was 6 days, right? So 6 days, I think, should be the T up top there. So E to the negative 6, and then we have divided by 1.44 times your half-life, right? And then RT, which is the activity after a certain period of time, well, after 6 days, we've reached 15 decays per second. So on the left-hand side, we should have 15, right? So let me just write that out here so you guys can see it. I'll erase some of the board here. Did I erase something?
Will we have to change the 120 and 15 to be decay per day since it's decay per second?
Yeah, I'll get to that here in a second, but yeah, you're on the right track.
So we have 100, so this is RT, right? It's the activity after a certain elapsed time is equal to R0, the initial activity, times E raised to the negative time elapsed. So this is the total time elapsed divided by tau, which is our time constant. This tau is equal to 1.44 times the half-life, right? So we can expand that out to just be 1.44 times T1/2, which is the half-life, right? Now, we started off at 120 for our initial, right? And then for our final, we ended up at like 15, right? 15 decays per second. Now, essentially, we're just trying to figure out what this T1/2 is, because we know the total time elapsed, we went from 120 to 15 in 6 days, right? So we just have this negative 6 up top here, so we're just solving for T1/2. That's all we're solving for. So
Thank you.
you can divide over the 120, right? You can do that, and then you can just take the natural log of both sides, right? So 15 over 120, you get like 0.125 here on the left, and that's equal to E negative 6 over 1.44 T to the 1, or T1/2 basically, right? Now, what do I want to do? So, yeah, take the natural log of both sides, right? ln of E is just 1, right? Now, when we take the natural log of this whole thing, remember that with natural log properties, whatever you have as your exponent can be pulled out to the rest of the equation, right? So you can just have like negative 6 over 1.44 T1/2, and then multiplied by ln E. It's the same thing. And ln E is just 1, right? This becomes 1. And then you're just left with ln of 0.125, right? So this is like negative 2.08 on the left-hand side here. And then we're just solving for T1/2, right? You can just multiply over this stuff here and then divide over again. So that times 1.44 is gets us around like negative 3 roughly, right? Negative 3 T1/2. And that's equal to negative 6 on the right-hand side. And you can just divide over the negative 3, right? And the negative will cancel out. And you're just left with your half-life as being 2 days. Now, you asked a really good question, whether we have to like convert things to like seconds and whatnot. Really, the only time we will want to like convert things into seconds, right, is if we're looking at like standard values for the activity. So if they're asking us like, I don't know, if they want us to find, so if they want us to find like the activity after a certain period of time, then that activity has to be in decays per second, right? So we want to make sure that, like, what do I want to say? Keep forgetting. Oh, I lost my train of thought. Okay, hold up. Oh, man.
I'm just wondering because I kind of already converted it into days, so
Mhm.
I was wondering, can I get the same value if I use these values?
So hold up, what did you do exactly? So you did 15 decays per second, okay.
Would I get like the same? I'm just wondering.
I'm not sure if you would, but 150 15 becquerels, 120 becquerels. My only issues with like, that's weird. Cause yeah, they gave this in days, so Huh. I'm gonna go back and double check something here in the reading. So you have some problems in the reading that will be like decays per minute, and they'll have the half-life being like in years, and they won't like do anything about that. I'm not sure, to be honest. I'm trying to double check this with the reading. Oh my gosh.
No worries.
I'm just double checking. It's because it's a really good question.
Because I got it.
You got the
value.
same thing? You got the same value? So, okay, so you had your decay per day, and you just did the same. That's weird.
We did it.
I suppose we did. But I'm curious as to why that works. Maybe I'm just missing something, because like if you have 120 on one end, and then you multiply by e and raise to the negative 6 over 0.44 times. Huh. Because for some reason I forgot the scenario as to where like we would be multiplying and having things in seconds. I'm going to reference the first exam as well, because I know there's a similar problem to this one. Yeah, so like we did problem 6, for example, on the first exam, and they wanted you to calculate the activity, right? And so they did things in decays per second, so you actually had to multiply out. Even with the half-life, they had the half-life of like 5,000 something years, and so they wanted you to figure out the activity in decays per second, and you had to multiply by how many seconds there were in a year to figure that out. And so I'm just a little unsure as to why you could just plug it in like that and not have to worry about seconds. And I'm also curious as to how that worked. Let me double check. Can I see your work as well, like on the paper, if you don't mind? Or is it okay? that's odd. I'm not sure if that's a mistake with the key or something. Like, why in the activity equation, like, where we have this problem, it's problem 6, where we're trying to calculate the half-life, right? But the way they have the equation set up is their activity values are in decays per second, but the time elapsed is in days, and they want the half-life in days. So should you be converting the time elapsed to seconds, and then, or not the time elapsed to seconds, but the decays per second, like the activity, to decays per day then, or decays per day, and then that's how you can figure out the half-life? The weird thing is that if you do it either way, like, you get the same answer. So I'm not sure if that, like, maybe I'm just missing something. You know what? I'll just move on from this problem. We have a lot to cover anyway. So I'll look into this one a little bit more and see, like, what's up with it, because I'm not 100% sure. But yeah. Yeah, I'm getting to the point where, like, I'm losing my ability to, like, think. Problem 7 is magnetic fields, right? So we have 2 long wires that carry current in the plane of the page. One wire will have the direction kind of going upwards, right? And the other wire will have the direction going to the right. And then it says consider a point P located 2 centimeters from wire 1 and 3 centimeters from wire 2. So here's wire 1, here's wire 2, and then here's point P. Point P is 2 centimeters away from wire 1 and 3 centimeters away from wire 2. And they want you to, so they say the current in the first wire is 5 amps, so I1 is 5 amps, and then I2 is 10
which
amps.
Which equation will we use
for this one? So part A is asking what is the magnitude and direction of the magnetic field due to current 1 at point P. So, due to current 1 at point P. Yeah. So we're looking at the magnetic field generated by that first wire, right, at point P. So we look at the magnetic field equation for a current carrying wire, which is the magnetic field is equal to the permittivity constant times your current divided by 2 pi r. So it kind of looks like that. And I can show you which one here. This one right here.
Okay,
magnetic
but
field of a wire.
what would be our R?
Our R is the distance from that wire to a specific point that we're looking at. So in this case, it's just point P, right?
That would be like the radius, or
It technically is the radius, right? That's how they kind of like define it, or like the distance across from that wire to that point. So from the wire to point P, it's 2 centimeters relative to that wire 1. So our radius is 2 centimeters. Remember, we have to have things in SI units. So instead of 2 centimeters, you have 0.02 meters, right? And we have our permittivity constant as well. So that's 4 pi times 10 to the negative 7, and then multiply by your current for that first one. That was what, 5 amps? And then divided by 2 pi times the radius, which is 0.02 centimeters. Or 0.02 meters, my bad. And that'll give you the magnetic field due to current 1 at point P. So that just tells you, like, or is asking, like, what does point P feel from wire 1? And so you'd calculate your magnetic field based on what wire 1 generates. But yeah, and it's also obviously like the distance between wire 1 and point P. So you can't use like that 3 centimeter distance. You have to use the 2 centimeter one. But yeah. Does that make sense so far?
Mm-hmm. And all this is recorded, right? Because I know I was here earlier and. I know I was.
Yeah,
Here.
everything's recorded.
Right. Let me make sure.
And then if they were to ask you, for example, what the direction of the magnetic field is, so we can do the right hand rule again, right? So if the current is pointing upwards, right? Thumb upwards, and then you wrap around, because we're at point P is to the right of the wire, so you wrap around this way. So that goes in what direction? Into the page, right? So it goes into the page on the right, and then on the left-hand side, what direction does it go? Out of the page, right? So it goes out of the page on the left into the page on the right. So that's if they were to ask you. Actually, they do ask you the direction, my bad. So it should be, you should have that into the page there. But yeah. With that being said, our magnetic field, we can go ahead and calculate that out. 4 pi times 10 to the negative 7. And then multiplied by 3 amps. And then divided by 2 pi times 0.02 meters. So that gives us 3 times 10 to the negative 5 for our magnetic field. 3 times 10 to the negative 5 Teslas. Is that what you got as well? 3 times 10 I got 3 times 10 to the negative 5.
Oh, we would convert from centimeters
You're
to
good.
meters, right?
Yep.
Sorry.
No, you're
It's
good.
just I've gotten used to just leaving it as is with some reasons.
Yeah, for the image stuff. Yep. Now, they'll ask, what is the magnitude and direction of the magnetic field due to current 2 at point P? So it's just kind of a repeat. It's just that you're doing current 2 now, or wire 2. So you still have your magnetic field is equal to your permittivity constant times your current divided by 2 pi r, right? So in this case, the radius that we're using is that, was it 3 centimeters distance? Yeah. So that 0.03 meters is our r now. Use the same permittivity constant, same current, and then that is how we can figure out the magnitude of the magnetic field. Now, if we wanted at point P to figure out the direction now, thumb to the right, that's the direction of the current, right? And now we're looking for how it points above the wire, above that second wire, at point P. So if I just like thumb to the right, what direction is it going? Above the wire, out of the page, right? Now if it was below the wire, into the page. So it goes into, and then it curls back around, and then out of the page above the wire, right? So that's out of the page, right? And then we can calculate here the magnetic field. We have 4 pi times 10 to the negative 7 times 10 amps, right? And then divided by 2 pi times the radius, which is 0.03 meters. Yeah, let me double check here. So did I? Wow. Okay, my bad. Let me go back and recalculate the first one because I wrote 3 amps instead of 5 amps. So it should be 5 times 10 to the negative 5. So the first one should be 5 times 10 to the negative 5. And then the next one should be 6.67 times 10 to the negative 5. Is that what you got?
Mm-hmm.
Okay, awesome. But yeah, and we already determined the directions. Now it says, what is the total magnetic field at point P? So this is interesting because we haven't had a problem like this yet, I don't think. So the way I like to do these types of problems where I'm finding the net electric or net magnetic field is to treat into the page as positive and out of the page as negative. So into the page is positive, out of the page is negative. You could do the opposite if you wanted to, but I feel like for some reason it's just easier to do into the page is positive and out of the page is negative. Plus, that's how a lot of the practice problems in the reading are based, and how I've personally solved a lot of these problems. And I don't mean to flex, but like I got a lot of these problems right. So like I know what I'm doing to a certain extent. But into the page positive, out of the page negative, I think is your best bet. And so B net, or net magnetic field. So we take into the page, which is B1, right? Make that positive, and then subtract B2, right? B1 minus B2, because B2, the magnetic field of the second wire was out of the page at that point. So that was negative.
So B2 would be negative because the force is pointing.
Oh, we don't use the
Right hand rule.
Yeah, we don't use the one like for the particles and stuff. So we use the other one, just the wrapping your fingers around. So like here you can see that your thumb is moving upwards, right, for the current, and then it kind of goes into the page, this side here, right? And then if you do this one, your thumb is to the right, and then on that end right here it goes out of the page. See, so into the page positive, out of the page negative. So we just take B1 minus B2. So for B1 we had 5 times 10 to the negative 5 Teslas, and then minus 6.67 times 10 to the negative 5 Teslas. And then if we just subtract that, right, 5 minus 6.67, we should get like negative 1.67 times 10 to the negative 5 Teslas. And they're looking for the magnitude, right? So magnitude in this case, just take the absolute value of that, and you're just left with 1.67 times 10 to the negative 5 Teslas. Now, because they're asking for direction, remember what I said? Positive is into the page, negative is out of the page. So in this case, it's out of the page. Does that make sense so far?
For part 2?
For part C, yeah. Problem 7, part C.
And you said it's into the page?
It's out of the page for the net magnetic field.
For I2, right?
I'm talking about the net magnetic field.
Oh.
It's into the page for I1, out of the page for I2,
Okay.
and then out of the page net for both of them. But yeah, so into the page positive, out of the page negative. I'll write that down here as well. Into page positive, out of the page negative. But yeah, and like I said, if you had it either way as well, that's fine, but that's just what I prefer, and I think that's probably the best bet. But now we have part D. So last part for this problem. It says, what would the current I2 need to be for the net magnetic field to be 0 at point P? So for net magnetic field to be 0, it means that the two magnetic fields have to cancel each other out, right? So B1 has to equal B2, right? So if B1 is equal to B2, we're trying to figure out the current I2 needs to be, right? We know that B1 is equal to permittivity constant times I1 divided by 2 pi r, and then B2 is equal to the permittivity constant times I2 divided by 2 pi r as well, right? Well, you can kind of cancel out like the permittivity constant and the 2 pi on either side, because those will be constant. There's no reason to like rewrite them again, because once you multiply and divide those values over, they'll cancel out. So you're left with essentially like I1 over R1 is equal to I2 over R2, right? So we want to figure out what I2 is in order for them to be equal to each other, right? So I1, we know that I1 is 5 amps and R1 is that 2 centimeters, right? You don't have to convert to meters in this case because they're just ratios. So you can just do like 5 amps divided by 2 centimeters, and that's equal to I2 divided by 3 centimeters. And that'll give you I2 is 7.5 amps. Does that make sense so far? Any questions?
So we could just simplify it to just current over R is equal.
Mm-hmm. Yeah, because you can, the permittivity constant and the 2 pi, they're gonna like, once you multiply things over, they're gonna cancel out anyway.
So you just multiply both sides by 3 to take out the denominator, and then you got 7.
Yeah, you can just take out the denominator, take out the permittivity constant, because there will be constant on either end. You're just left with I1 over R1 is equal to I2 over R2.
So you're just setting them equal to each
Yeah,
other?
you set them equal to each other. And then you know what I1 is, you know what R1 is, and you want to figure out what I2 is given R2. Basically, yeah, you're just trying to figure out like what combination of current and the distance is going to give you an equal magnetic field, basically. The ratios have to equal each other. Makes sense so far? Any questions about this stuff?
Yeah.
Okay. Move on to problem 8 then. So problem 8 says an oil film with index of refraction N oil is equal to 1.46 floats on a pool of water. N water is equal to 1.33 as shown in the figure. A light ray traveling in air, N air is equal to 1, is refracted through oil and water. Right? So we have N oil. The index of refraction of oil is 1.46. Index of refraction of water is 1.33. And the index of refraction of air is just 1.
Did you get
Hmm?
this? I just want to make sure.
Yep. And you can see in the diagram there, like you have the, what do we call the 60-degree angle there? Like, or at least what do we call that first ray, that first light ray?
Incident ray?
The incident ray. So what is that angle called then? Same beginning. Incident angle, right? So incident angle, incident ray. So our 60-degree angle there is our incident angle of our incident ray coming through air, right? Yeah, go ahead.
Would it help to calculate the critical angle? That way we know if there's anything being refracted, or is it just because of the diagram we know that there's refraction?
Just because of the diagram in this case, we know that there's refraction, and at the same time, like for critical angle stuff, unless they mention to you like that there is, or there's going to be a possibility of total internal reflection, then you calculate for the critical angle. Or if they're just asking you like hypothetically, like what would be the maximum like index or maximum incident angle that would cause like total internal reflection or something like that. But yeah, based on the diagram, you're just considering that there's no total internal reflection, that you have some kind of refraction going on. So, and then you don't like solve for critical angle or anything like that until like they ask you for it. But for part A, they're saying find the refracted angle theta of the light ray entering the water layer. So, okay, so we're just trying to figure out the refracted angle, right? So it's just the angle between oil and the normal, or like that refracted ray and the normal line in oil. So if I draw this up on the board here, right? Erase again. So we have the air surface, right? Air coming in like this. Then we have oil. Then we have water, right? So the incident ray is coming in like this, and it's getting refracted a little bit downwards like that, and then might get refracted even more like that with water, right? So the normal line here, the normal line is defined as the line that's going to be perpendicular to the surface at which the light rays are hitting, right? So the light rays are hitting what type of surface here? Vertical or horizontal surface? Horizontal surface, right? So the normal line would be the vertical line here, in this case, right? So this is our incident angle, the 60-degree angle here, and then this, relative to the normal line here, is our refracted angle, which is what we're trying to figure out, right? So they're asking us for the refracted angle of the light ray entering the water layer. Then they're not only asking for like this part, but they're also asking kind of like for this angle right here. But yeah, so what does this mean, right? So we have this incident angle that's going to get refracted in the oil to some other angle. That angle, right, is going to be the same angle here, because you have two like parallel lines, these two parallel normal lines. And if you remember from geometry, like if you see like two lines, parallel lines like this, and they kind of like form a Z shape, then these angles are the same, right? So in this case, this angle right here, whatever we get for this angle is going to be the same one here. And so that's going to be like our incident angle between oil and water. and then we use that angle to figure this one out here. So what equation can we use to figure out like relationship between index of refraction and incident angles and stuff like that?
N times sine theta is equal to N times sine theta.
Exactly. So that's Snell's law. So that's N1 sine theta 1 is equal to N2 sine theta 2. And it's probably better to like write your subscripts based on the different layers. So like you have N air, sine theta air, and that's equal to N oil, sine theta oil, right? Okay. Well, we have N air, that's 1. Sine theta is sine 60 in this case because that's our incident angle. And then N oil, right? N oil is 1.46. And then sine theta oil, well, sine theta oil is what we're trying to figure out, right? So we have sine 60 divided by 1.46. What does that give us? It gives us 0.59. And that's equal to sine theta oil, right? Well, we actually just want the angle, right? So how could we get rid of this sine?
Reverse sine.
Inverse sine, exactly, right? So if we take inverse sine of 0.59 and inverse sine of theta oil, then that cancels the sine out, and you can get just the theta. So if we take inverse sine of 0.59, that gives us theta oil, which is what?
36?
Yeah, I think so.
And then we can use that angle to set oil and water equal to each other?
Yeah, I got 36.16 degrees exactly.
Yeah, I got that too.
And then that's your angle now. That's your angle of incidence between oil and water, right? So if I'm drawing this here on the iPad as well, just so you guys can see that, right? Here's air, here's oil, here's water, right? So we come in like that. Here's refraction, and then here's another refraction again, for example. So everything's kind of based on this normal line here. So you have 60 degrees is your incident angle for between air and oil. And then you have, really what you see here is if we could kind of draw like another normal line, then whatever angle we have here, which is our refracted angle, that 36.16 degrees.
This would be. You okay?
Yeah.
You want to take a break?
No, I'm good. 36.16 degrees is the refracted angle there between air and oil. And then that same angle is going to be right here because you have two parallel lines essentially. And so that's kind of geometry rules right there. And so you can see that this angle, 36.16 degrees, is also that angle of incidence between oil and water. And then essentially we're just going to be doing another round of Snell's law. So we're going to be doing like N oil, sine theta oil is equal to N water, sine theta water, right? And then N oil we said was 1.46, right? And then sine of 36.16 degrees, which is our incident angle now. And then N water is 1.33, and we're just sine theta of water, which is what we're trying to figure out. Go ahead.
Real quick for the next question.
Mm-hmm.
Is this?
Find critical.
I just want to make sure because I know I have to put this side. Find a critical angle. What is this side?
Yeah,
So this is
I think so. So yeah, we take 1.46 times sine 36.16 degrees, right? And then divide by 1.33, and then take the inverse sine of that. That should give us 40.4, I think. I think they have on the keys like 40.6, but kind of depends on how you round it and whatnot for that previous angle. If you didn't round at all, that's probably better. So just save your answer because that'll give you the most accurate thing. But as long as you have your work corrected, it's fine. So theta water is 40.4 degrees roughly. Now that's A. Part B is saying a second ray travels in the opposite direction. It is refracted at the water-oil interface, right? And undergoes total internal reflection at the oil-air interface, right? So it gets refracted between water and oil, and then it gets totally internally reflected between oil and air. So it says find the critical angle of incidence at the oil-air interface for total internal refraction to occur they wrote refraction, should be reflection. There is just a very simple equation that we could use for the total internal reflection, and that is that the critical angle that we're trying to figure out here is just equal to the inverse sine of like n2 over n1, right? So that just is like n2 should be your second material that you're going through, or that you would have gone through, and then n1 is your first material, right? So in this case, like between oil and air, what would be our first material and what's our second material?
Water's the first material and oil is the second.
Between oil and air.
Oh. Wait.
So it'd be oil and air?
Yeah, so between oil and air, which is the first material and which is the second, technically?
Water's the first material.
Water's the first material in general. I'm saying like once we get to oil and air, like just between those two,
Oh.
like let's say if we let it refract,
Is oil?
oil is the first material and then air is the second material, right? So for air we have 1 as our N2, and then for oil is just 1.46. So inverse sine of 1 over 1.46 is going to give us our critical angle as well. So if we do that,
Again, right?
we should get 43.2 degrees for your critical angle, right? Alternatively, and I think what you did, Matthew, as well, is that you could think about this in a very like logical sense, and what is in total internal reflection. So basically what happens is that you reach a certain angle, right, of incidence to where the refraction that's caused is now like 90 degrees, right? So essentially what happens is like you have, and I'll draw this on the board here in a sec, but you have this angle of incidence coming in, and then between that interface, now the angle is just completely flat with the other surface. Once you kind of have that, or like once you get past that point or just at that point, is your critical angle. So like I said, if we have this incident angle like this right here, then you reach total internal reflection when the other ray that's being refracted is just essentially just going across the surface of the other like interface or the other medium, right? So that's when like this angle here is 90 degrees. And this would be like your critical angle, right? The critical angle is when you reach that 90 degrees of refraction on the other end, right? So what you can do is just use Snell's law again. You do n1 sine theta 1 is equal to n2 sine theta 2, with n2 obviously being in second material, so that would be air. Sine theta 2 would be sine 90 degrees, because that would be the maximum like refraction. And then n1 would just be your oil, and sine theta 1 would actually be sine of your critical angle, right? So your critical angle is on the left-hand side, and the right-hand side would be like your maximum total refraction, which is the 90 degrees, right? So you could do it either way. But yeah, and then for C, what is the smallest angle critical of incidence at the water-oil interface that results in total internal reflection of the ray at the oil-air interface? So this is just asking for, what is it? Yeah. So it's asking for the minimum angle required, the minimum incident angle from the water, because remember we started off from water and then we went to oil and then air. So it's the minimum angle here that we start off with that would cause this critical angle and then cause total internal reflection. Does that make sense? So first we were looking what the critical angle was, but in order to have this critical angle, it had this ray had to be refracted by the ray before it, right? So like you might have had this ray going like this, and then it got refracted to that critical angle. How do we reach that critical angle? Well, we had to have some kind of angle here from the beginning, right? So once again, you can just do Snell's law. You can say n1 sine theta 1 is equal to n2 sine theta 2. n1 would just be the water's index of refraction. Sine theta 1 would be that minimum angle required. n2 would be the oil. And then sine theta 2 would be like sine of the critical angle, right? Because we want the critical angle to be the angle that we achieve, and then we're trying to figure out the angle that we started off with, right? Does that make sense?
So we could just plug in the critical angle we got before and just...
Yeah, so you have n1 sine theta 1, right, is equal to n2 sine theta 2, and then you have n2 is your what? That's your oil, so that's 1.46. and then times the sine of the critical angle that we got before, which is 43.2 degrees. And that's equal to N1, which is our water, and that's 1.33 times sine theta 1. Theta 1 is what we're trying to figure out. So if we just solve this out here, 1.46 sine 43.2, and then divided by 1.33, and then take the inverse sine of that. That should give us 48.7 degrees as the minimum angle required to cause that critical angle, right? So that means like we have to come in at an angle of 48.7 degrees in order for this to be refracted to that, what was the critical angle again? 43.2 degrees, right? So if we had 48.6 degrees, we're not reaching the critical angle, right? If we had 48.8 degrees, we're now past that critical angle at that point, and now you're just experiencing total internal reflection, right? So that's the minimum angle required to reach this critical angle to cause total internal
So basically,
reflection.
finding the angle that goes over that critical angle to cause total internal reflection, basically. The angle that starts off that.
Yeah, the angle that starts it off.
Would it be okay if I rounded it to 49?
Yeah, that's fine.
Okay.
No worries. I prefer personally just to have like decimals in, just to make it more accurate, but yeah, it doesn't matter. But that's problem 8. Problem 9 is left here, okay. So problem 9, write this over here. Okay, problem 9. A patient has a shortened eyeball. The retina in the patient is located 1.89 centimeters behind the eye lens. The shortest focal length of the eye lens is 1.85 centimeters. Okay, so they gave us basically the length of the whole like eye right there, right? And the focal length, the shortest focal length is 1.85 centimeters. Now they're asking for the near point, which is the shortest object distance for an image to form on the retina, right? So in this case, we're using the eye lens as the lens that we're obviously kind of basing things on. So relative to the lens, right, what would be the focal length of the retina? Remember the focal length is measured from the lens to
1.89 or 1.8?
Yeah, 1.89 or 1.85. My bad. Yeah, 1.85. Because we're basing things on the near point.
Because it's a near point, that means would it be the DO or the DI? Because I know for near point, one of those values has to be negative.
That's
So
if there's an object.
yeah, the 1.85 is for our focal length, and now we're trying to figure out the distance of the object at the near point, right? So we're trying to figure out like how close you can bring this object to where the person can see it. So we're looking for DO basically, and we know that the image forms on the retina, which would be at a distance of 1.89 centimeters, and the
So basically, our DI would be the 1.89.
yeah, exactly, and that would be a positive image distance because the light rays will actually converge there, because that's obviously how you would see, right? You have to have light rays to converge there, so the image has to be a real image. And so DI is 1.89 centimeters because that's where the image is going to be forming on the retina, right? That's the image distance, that's where the image forms. Focal length is going to be 1.85 centimeters, which is the focal length for the near point. And then we're figuring out the object distance, which is the closest you can bring the object, or the shortest object distance for an image to form on the retina. That's what we're trying to look for. So with that being said, we can just use the thin lens equation, right? So we have 1 over f is equal to 1 over do plus 1 over di. 1 over f is 1.85 centimeters. 1 over do is what we're trying to figure out. 1 over di is 1 over 1.89. And then we can figure out do. Now, because the what's it called? The light rays will actually converge on the retina like that, right? And cause a real image, then what kind of lens are our eyes? In that sense, if it's causing a real image to be projected on the retina.
Wait, like what kind of lens?
Yeah, like converging, diverging. Like if it causes a real image like that. Yep, converging. But yeah. And then once we do that, right, we can just solve for DO. 1 over 1.85 minus 1 over 1.89. And then that should give us like 87.4 centimeters.
The retina would serve as the distance from the object, correct? DO.
Retina serves as the image distance.
Oh, image distance.
Image distance.
Oh,
so the
we're
1.89 centimeters is the
so
image
we're trying
distance.
to find the DO.
Yeah, you're trying to find the DO. You're trying to where that object is located relative to the lens. But the retina, the 1.89 centimeters, is the image distance because that's where the image actually forms, right? So that's how we see our image is projected onto our retina. So 1.89 centimeters is the image distance, and that's a positive value because it's a real image that's formed onto our eyes. Otherwise, like that wouldn't make sense as to how we would see, right? But yeah, and that's the object distance is 87.4 centimeters. B is calculate where the image of an object located 25 centimeters in front of the eye would form, right? So now we have an object that's located at a distance of 25 centimeters away with the same like focal length from before, and now we're just trying to figure out where the image would be located, essentially. So once again, we use the same equation, the thin lens maker equation, or thin lens equation. So 1 over f is equal to 1 over do plus 1 over di, 1 over 1.85, and then 1 over do is what? Do is the 25 centimeters, plus 1 over di, and that's what we're trying to figure out. So 1 over 1.85 minus 1 over 25, and then we solve for di, and that should give you approximately around 2 centimeters for your image distance. Now, does that make sense so far? Any questions, guys?
So,
Oh, yep, yep. Nice. Oh man, I'm tired.
I saw it.
You're
kidding.
What?
I saw it. I'm stuck.
Oh my god.
Wait, what?
Bro, you have like third
We'll be fine. I'll figure it out.
40 minutes.
So,
Did he ever say what he's trying to do?
No.
alright, so part C now. If everyone's on the same page, we can just probably just move on to part C. So it says, is this in front of or behind the retina? Based on this information, explain if the patient would need eyeglasses with converging or diverging lenses. So we know that the image distance, the image that actually forms, is a distance of 2 centimeters. Is that going to be behind or in front of the retina?
This would be in front of the retina, no? Wait, no.
Not quite.
No, it's behind.
Behind, right? Because it's past that 1.89 centimeter length.
Because
right?
if it's not within the 1.8, then
Exactly.
yeah.
Then it would be, yeah. So if it's not within that, it's behind it. So
They
that
need-
means that the image forms past your retina and you're not able to see it, right?
so,
So, yeah, go ahead.
so basically, if it's like, because it's 2 centimeters, and because our retina is 1.89 centimeters, then basically anything greater than that will be behind it, but anything like less than that will be in front of it.
Mm-hmm. It'll be in front of it.
So basically, they need diverging lenses, no? Because it's past that point.
For this, you would need converging lenses because they're like, the way I think about it, I just explained this to my brother the other night, but so like if you have this where here's like where you need it to converge, this is where you need it to converge, and this is where it's actually converging, you want to use a converging lens to connect it to the actual focal point,
Because
or like
of
the actual like place that you want to
because of
focus it
how
on.
far it is.
Yeah.
basically.
So it's like a converging lens will help connect it like earlier, basically, if that makes sense, right? Because it'll help converge it more, connect it more.
And you'll be able to see that image, basically.
Yep. Now, if you had where it's like, okay, here's where I actually want to connect it. I want to use a diverging lens to divert away the rays to where they kind of go away from each other a little bit more. You divert them away from each other to where they're now converging at a place farther down the line.
So if it was within the 1.89, that's when we would use the diverging lens.
Yep, you would use a diverging lens in that case to divert the rays away from each other and then have them connect farther along in the retina to where you get to that 1.89 centimeter length. Now, like you said, if you have it past where it's like 2 centimeters or 2.1 or whatever, then you want converging lenses so it connects them earlier.
Yeah.
Does that make sense?
Yeah, that's, thank you.
So, yeah, let me write that down. So we have this image forms behind the retina because it's past the 1.89 centimeter mark. And then we would need converging lenses to effectively like connect the rays earlier, so that they converge properly at that point. Because we're essentially converging late, we want it to converge early, because it's going past that 1.89 centimeter length. Does that make sense? So image formed behind the retina, so the patient is converging lenses. Yep. Must converge at a point. They must converge at the location of the retina. So they're converging past it currently, and you want it to converge it at the retina.
So converge at the retina, that's behind.
Yeah, so we want it to converge at the retina. Part D now is saying, determine the focal length of the eyeglass lenses to restore vision for an object located 25 centimeters in front of the eye lens. The eyeglasses are worn 2 centimeters in front of the eye lens. They should create an image of the object at the near point you calculated. Make sure to use the correct sign for all distances. So, okay, so they want us to figure out the focal length of the eyeglass lenses, right? To restore vision for an object located 25 centimeters in front of the eye lens. So the object distance is 25 centimeters, right? And then, what did I want to say?
Should we first calculate for the lenses first? Like,
I'm trying to think. Should create an image of the object at the near point you calculated. So essentially they're just asking you for like, okay, we want to produce an image using those glasses before it actually comes to our eyes. So they want us to produce that image that you see over there to the left at that near point before it like gets projected onto our eyes, right? So it's asking like, okay, how can we produce that image at that near point, basically? So with that in mind, right, we know that the object distance is always measured relative to the lens or the mirror that we're looking at, right? So in this case, it's not 25 centimeters, but rather what should it be? Measured
23?
relative to the glasses. 23, exactly, right? So 25 centimeters minus 2 centimeters gives us 23 measured relative to the lens or to the glass. And so that's 23 centimeters for object distance. And then for our image distance, we have that, and that is, hold up, what do we have that as?
DL?
Image distance we actually got from earlier in the problem, right? So we had the image distance at the near point was 87.4 centimeters, remember that? So, from part A, we said that the object distance, like at the near point, was 87.4 centimeters. So our near point is 87.4 centimeters. They just want us to reuse that. Now the idea is that it was 87.4 centimeters measured from the eye lens itself. So measured from the glasses, what should it be?
So wait, what would we use for
For DI, we're using, since we're looking at the image distance, which is at the near point, we're using the near point distance, which was 87.4 centimeters from part A. Because remember, we calculated where this was.
Oh, right.
Yep, exactly. But that's measured from the eye lens itself, like the eyeball itself. Now, measured from the glasses, what would the actual image distance be? 85.4, right? So our image distance is 85.4, but also keep in mind that, what did I want to say? So we have, okay, yeah. These should be converging lenses, right? So if they are converging lenses, let's forget about the eyeball for a second. If these are converging lenses, like the glasses are converging lenses based on part C, should you be seeing an image form on the same side as the object?
What's the question?
Normally? Yeah, I can repeat it. You have your eyeglasses, right? We said those were converging lenses to fix the person's issues, right? So if they're converging lenses, remember what we said about converging lenses? You could either form what two types of images could you form?
Virtual or real.
Right? And when can you form a virtual?
If it's in between the focal point and the lens itself.
Now, we don't know what the focal point of the glasses are, right? That's what we're trying to figure out. But we know that for a converging lens, the rays actually go through the lens, right? They actually go through it. And they form an image, a real image usually on the other side, right?
Yes.
The time where you have an image formed on the same side as the object is when you have a virtual image, right? So a virtual image, like, 'cause that's the thing, like, if I'm, like, I guess, I don't know how to explain it, but because it's a converging lens and the rays actually go through the lens itself, those rays should go through, get refracted, and then they connect on the other side, like behind the lens, right? But in this case, you're forming the image even behind the object, which is weird, that's unusual, and that's because, right, based on what we know and what we understand is that, okay, well, we can assume now that this object is located probably within the, like between the focal point and the glasses, right? So even without knowing that, we realize that with a converging lens, having the image formed on the same side as the object, we know then that the image has to be virtual. It cannot be real because it's on the same side as the object, right? So our 85.4 centimeter distance for the image is actually negative 85.4 because we know now that it's a virtual image because you can't have an image formed on the same side as an object for a converging lens like that unless it's a virtual image. So yeah, go ahead. Did you have a question?
Yes.
Let me go ahead and solve it here real quick. So we have image distance is negative 85.4. So we have 1 over f is what we're trying to figure out here. 1 over do, that's 23. And then plus 1 over negative 85.4. So
a DI would be negative?
yeah. So
And
that's
you-
because it was virtual, right? So we can't, like, if you have the image formed on the same side as the object with a converging lens, then that means it's a virtual image. Otherwise, a converging lens would produce an image on the other
I knew
side.
because it was near point and half.
Yeah. So 1 over 23 plus 1 over negative 85.4 gives us 0.032, and then we can just flip that over, and we get 31.48 as our focal length. 31.48 centimeters. But yeah, not too bad. You could also confirm it another way. So looking at the object in the image, do we see that it's been magnified? Has it gotten bigger? Has it gotten smaller? Got bigger, right? So, yep, 31 centimeters. So we got bigger. So based on the magnification equation that we know, it's negative di over do, right? So also at the same time, look at the object and the image. Have they been flipped, or are they same? Are they both upright?
Both upright?
Yeah, both upright, right? So upright means you have a positive magnification. So in order to have a positive magnification, given the fact that it's negative di over do, that means that you had to have a negative di, because negative will cancel out with a negative and give you a positive, right? So it's another way of checking as well. But that's it for problem 9. Last thing is problem 10 now. That's problem of the day. So, okay, let's see here. So it says the cobalt-60 isotope undergoes beta minus decay with a half-life of 5.272 years. It says complete the following reaction, determine Z and A. So that's what I was talking about earlier. We have to determine what Z and A are. Z is your number of protons, A is your atomic mass number, right? With beta minus decay, your atomic mass number doesn't change, but your protons will increase by 1, right? So in this case, you simply just like rewrite the equation. So 60 and 27 cobalt breaks down into then 60, 28 nickel, right? Plus an electron plus that there. So with the alpha decay, beta decay, all that stuff, I highly, highly, highly recommend going back to the reading and like looking at that, having that memorized to a certain extent, because me personally, looking at the formula sheet, it's kind of confusing. I don't know why, but like at just first glance, it's just confusing to me. So it's not too bad to like know, because what they have on the equation sheet, they'll say like, oh, it releases 2 protons and 2 neutrons and stuff, and then you have to like translate like, okay, what does that mean? Let me go back to the equation, figure that out. So if you can just like know that, okay, beta minus decay, A stays the same, Z plus 1, right? So you can just kind of like do those types of like calculations in your head, and you know that, and you have that memorized, as opposed to like referencing the equation sheet all the time, because you're gonna have like a whole problem like this where you have to do that. But I mean, yeah. So that's part A.
So
Yeah, go ahead.
the A would stay the same, the 60.
Yep.
But because of the electron, then our Z will need to be 28.
Yep. So you increase your Z by 1.
Alright.
It says a sample of cobalt-60. In a sample of cobalt-60, what percentage of nuclei has not decayed after 2 years, right? So this is just trying to figure out like how much is left after 2 years, given the half-life information that we have. So we can use the half-life equation to figure out how much is left. And so like we know our half-life equation is some nt is equal to NO, our original amount, our original nuclei amount, times e to the negative time elapsed divided by the time step there, or the time constant there. So in this case, the time elapsed is 2 years, so that numerator should be 2, negative 2, and then our denominator, the tau, should be 1.44 times the half-life. So 1.44 times, 1.44 times t 1/2, or 1.44 times the half-life. You have a question?
I am trying to. What exactly? If you're trying to find percentage, then that would be like x times the original.
So you'll get like, what did I want to say? Yeah. So you'll get the amount that's remaining here, right? Once you calculate like NT, whatever you get there is the amount that's left over, right? So that's the amount that's left over. With that being said, I'm gonna reference this back again. So, what did I want to say? Actually, hold up. So, oh man, okay. Yeah, okay. So the amount that is not decayed as a fraction, right, would just be the amount that's left over divided by the original amount. So whatever you find out for NT, right, let's say you get like 16 or something, and you started off with 20, then 16 is what's left over that hasn't decayed yet, that's what's left over, and then you divide by 20, which is what you started with, to get the percentage that has not decayed, right? And so in this case, what you can do is just plug in really just your half-life at that point, which is the 5.272 years. But let me see here. I just want to make sure. Yep. So you just plug in your half-life at that point. So yeah, go ahead.
So basically, NT and NO, they would just be there.
What do you mean?
Like it would just be.
Well, NT is what we're trying to figure out first, which is like how much is left over that hasn't decayed.
Oh.
So let's see here.
So then what would be my NO?
Your NO is what do I want to say? Yeah, so you would just divide over your NO, because NT over NO would be the exact percentage of what hasn't been decayed. So they don't give us an NO, right? They haven't given that to us, but we know that the stuff that's left over divided by the original stuff is going to give us the percentage that hasn't decayed. So more or less, like, here's the idea. If I started off with 20, right? And let's say my half-life is that 5 years, right? So after 5 years, I'm down to 10. After another 5 years, I'm down to 5. After another 5 years, I'm down to 2.5, right? So let's say after the first 5 years, right? After the first 5 years, I have 10 left over, right? 10 decayed, but there's 10 left over, right? Using that equation, NT is equal to NO and then e to the negative t over tau, right? NO is what I started off with. 20 is what I started off with. 10 is what I ended up with, right? To figure out the percentage that hasn't decayed, well, this is the percentage that's left. Well, this is the amount that's left over, right? I have 10 things left over, and I started off with 20. So what percent is left? Or what percent has not decayed? Just be 10 over 20, right? Times 100. And so that's the idea there, where you're taking the amount that's left over that has not decayed divided by the original amount, and then multiplied by 100 to get the percentage that hasn't decayed. Because this equation always gives you the amount that's left over that has not been touched yet, right? So, like I said, if you start off with 20, and after 5 years you end up with 10, right? You have 10 things left over from an original amount of 20, right? So I want to figure out how much or what percent is left, which would be 10 over 20, right? That's the percent that's left. That's how much I have left. So in this case, they don't tell us what the original amount is, right? So it's hard for us to figure out what the final amount is, but that's not what we're looking for. We're essentially just looking for what percent is left, right? And what percent is left is just taking what is left over divided by the original amount. So if we just divide this over, NT over NO, that's the percentage that we're looking for. And we know the rest of this, right? We know the rest of that. So we have e to the negative 2 over 1.44 times the half-life. If we figure that out, and then we can set that equal to NT over NO, right? Then we can figure out our half-life, or our, what's it called? Our percentage.
So then did I calculate this right?
Yep. Looks good to me. So 1.44 times 5.272. And then you'd be left with this negative 2 divided by that 7, is that 7.58? And then well, hold up, where are you getting a negative at from?
Because isn't it negative t over delta?
Yeah. So that's fine though. But wait, doesn't make sense. So e to the negative 2 over 1.44 times 5.272 Oh, but that's fine though. Because this will be a percentage, like this will be like a fraction or something, like 0.4, and that'll give you a negative value anyway. So the negatives will cancel out, so you're fine.
As long as it'll just be, if I'm doing this right, it'll be 26%?
Yeah, you didn't even have to actually do the natural log stuff, actually. You could have just done e to the negative of that. You didn't have to do the natural log. Because this is what we're looking for. Just the nt over no part. So, like nt over no is equal to e to the negative 2 divided by 1.44 times 5.272. And that gives us what? 0.768, or like 77% if we multiply by 100. Now, the answer key for this is wrong. I'm fairly certain it's wrong because I'm going by what I had on my exam, and I got full points for this part of the problem, and I don't see the same work being done on this end here. I think they just made a simple mistake here with the tau, I think, but yeah, you should be getting like closer to like 77%. They got like 50.
I got 76.
Yeah, 76. They got like 49 or something like that, which is not right.
Okay.
But yeah.
Yeah.
Yep. Exactly. But yeah, hopefully that makes sense so far. What else? So we have C now. Right. C is the last. There's D as well. But C is, and says in 1 gram of pure cobalt-60, there are 1 times 10 to the 22 radioactive nuclei. Determine the activity R0 in decays per second of this pure sample. Right. So they want the activity, which is the R value. And they're giving us the total number of nuclei that they have, which is 1 times 10 to the 22. And they want us to figure out things out in terms of like decays per second, right? So nuclei per second, basically. So you have that number of nuclei, and then you just divide by tau, right? So you have your...
So this would just be our NO?
Yeah. So it would be NO divided by tau. In this case, the NO was like the 1 times 10 to the 22. And so with that being said, we have 1 times 10 to the 22, and then divided by the time step, right? Or the, not time step, but the tau. So they gave us what? It's 1.44 times the half-life, right? So 1.44 times the half-life of 5.272. That's the tau. And then from that, we can get our, that would be in years. But here, we have to have things in decays per second. So whatever years you have, we have to convert them to seconds. Exactly. So listen up real quick, because this is really important. Definitely, I'd say have this memorized, because it's not on the equation sheet. It'll save you so much time on the exam, especially for a problem like this. And since it's one of the last problems, you're probably going to be rushing to do it. So number of seconds in a year, 3.15 times 10 to the 7th seconds in a year. Write that down somewhere. Make sure you have it like in your equation sheet. Store it in your calculator if you want to.
So that's 3.154
times 10 to the 7th. Not 4, my bad, just 3.15. There's no 4.
No, thought there was.
You're good. But it's really important to know this one, because especially it comes in handy with the activity stuff when you're trying to do things in decays per second, because they'll ask you to well, they won't ask you, but you have to know that you have to convert, like you have years for your half-life and stuff, you have to make sure you convert that back to seconds. So in that bottom, in the denominator, 1.44 times 5.272 years, you would have to convert that now to seconds. So you just multiply that whole thing in the denominator by 3.15 times 10 to the 7th seconds per year, to cancel out the years, and you're just left with seconds on the bottom. And I'm gonna go by my exam, and I got 4.18 times 10 to the 13th decays per second.
Closing in 10 minutes.
Okay.
Decays per second for that, right? So that's C.
This is like so, ooh.
1 times 10 to the 22, and then just divided by, you take 1.44 times the half-life, which is 5.272, and then multiply that as well by 3.15 times 10 to the 7th. It's like that whole thing in the denominator. And like I said, the answer key is incorrect, I'm fairly certain. But I'm gonna move on to D here real quick. So this will be the last part, so we can wrap this up. So it says, how long does it take for that 1 gram sample of cobalt-60 to have an activity of 2.4 times 10 to the 13 decays per second, right? So essentially, we're trying to figure out like the time elapsed to get to that specific activity. So it's like RT, we use the equation RT is equal to RO, which is our initial activity, times E raised to the negative time elapsed over tau, right? So RT is that 2.4 times 10 to the 13 decays per second that we want to reach. That's the decay, that activity that we want to reach, right? And then RO, which is our initial activity, is the amount that I just said, which is 4.18 times 10 to the 13th. 4.18 times 10 to the 13th is our initial. That's the correct initial value. And then that's multiplied by E to the negative T, which is what we're trying to figure out, divided by tau, which is 1.44 times the half-life, T 1/2, right? Now, let me double check here. I want to make sure. So, and yeah, this one, so I guess in this equation, you can simply just use the half-life in years. You don't have to convert it back to seconds or anything like that. So you just do like negative T divided by 1.44 times 5.272. Once you do that, you can just kind of isolate for the T on either end. You just kind of divide things over. Once you do, I think you get like 0.574 on the left-hand side is equal to E to the negative T over 1.44 times 5.272. And then you just take the natural log of both sides, right? And that's equal to E to the, or by that point, the E will cancel out, so you're just left with negative T over 1.44 times 5.272. And then your T eventually is just going to be 4.2 years. That's how long it would take. But yeah. Any questions about this stuff so far? None? No questions? All right. With that being said, I think I'll probably just end the session on that note. This recording will be uploaded on YouTube soon, later tonight. And then, yeah, we'll see if I can do a third exam review or not. I'm not sure, but we'll figure it out. But that's 2 exams so far that'll be uploaded on YouTube, so hopefully those are helpful. All right.